Hello, my name is Soygür, and I'm a graduate student at EEE department in Bilkent University. Today, I will present you the term project for the course EE 515 along CMOS integrated circuits, for which we were asked to design an 8-bit digital to analog converter IC. Throughout this video, I will go through the project requirements, followed by the design steps that I followed to complete the project. The project requirements are given in below. The digital to analog converter is designed using 0.6 micron CMOS process and the Cadence Virtuoso design software. It uses voltage mode R2R network topology. Its inputs are buffered with flip-flops while the output is buffered with an op-amp in unity gain buffer configuration. And most importantly, it displays monotonic behavior at its output. The project can be divided into three parts. In the first part, I performed the initial schematic design and simulations, while in the second part, I performed the corner analysis and Monte Carlo analysis to test the design under different process corners and mismatch conditions. And in the final part, I performed the layout design and post-extraction simulations. For this first part, I designed the op-amp first and configured it in unit gain configuration. I used default flip-flops of XFAB XC06 and connected them to transmission gates that are driven by the outputs of flip-flops that multiplex between VREF and ground voltages, which is then fed into the R2R network so that the analog output can be changed accordingly, and then it is buffered at the op-amp. This is the schematic of the op-amp. At leftmost, the current mirror can be seen, followed by the differential stage, then the common source amplifier stage, which also has a feedback for frequency compensation, and at the end, the power stage can be seen that lowers the output impedance so that this specified loads can be driven. And this is the schematic of the whole digital to analog converter. As it can be seen, the input is taken by the flip-flops, which is used to run transmission gates that control the R2R network. And these are the test results of the first part, which is subject to change when post-extraction simulations are performed. This is the open loop frequency response of the op-amp. It shows that it is stable with gain crossovers and phase crossovers shown. In the second part, I performed corner and Monte Carlo analysis, details of which are given below. I tested for different scenarios in typical mean, worst power, and worst speed conditions. For example, this is the output analog output waveform, which shows that with respecting digital inputs, the output changes linearly, although with spikes, it shows monotonic behavior. And these are the Monte Carlo analysis histograms. The histogram on the left shows that for different process variations, the output change at the given input shows that the output variation is small, and the right histogram shows that at 100 kHz with mismatch conditions, the PSRR is still above 50 decibels. And in the third part, I designed the layout of the op-amp and digital to analog converter. Then I used RC parasitic extraction to extract the parasitics from the layout and perform the final simulations. This is the layout of my op-amp. I used hand routing to minimize the area and make the design symmetric as much as possible. The op-amp layout is then used in the digital to analog converter layout. It can be seen at the top, configured in unity gain configuration. At the very bottom, the digital inputs are taken via a bus, which is then fed into the flip-flops, which control the transmission gates above. The outputs of the transmission gates are fed into the R2R network, which controls the analog output. Design can be seen using as minimal area as possible. Then I performed the final simulations with the extracted layouts. The phase margin is at 46 degrees, the DC offset is as 218 microvolts, and the power supply rejection ratio is at 53 decibels, and the monotone is still sustained even with parasitic components coming from the layout. This is the open loop response of the op-amp after parasitic extraction. It shows that it is still stable. And this is the unlock output when the most difficult switching is performed, showing that the digital to analog converter is still monotonic and design is successful. Thank you for watching.